Good morning, AP Calculus. Looking at anti-differentiation with partial fractions here. So in the AB course, you were given a problem at some point, something like that, where you had the antiderivative of x over x squared plus 3 dx. And you looked at this and you knew there was no reverse quotient rule, but you did know that if you had the natural log of an inside function, in other words, the natural log of ugly, then the derivative of that natural log of ugly would be a fraction. It would be the derivative of ugly over ugly. Okay, and that's kind of the situation that we had right here last year. You say, okay, well, if we use u substitution, we can make u equal to x squared plus 3, and the derivative of x squared plus 3, in other words, the du, would be 2x dx. So we have x dx, so we would just toss a 2 in front of that x and the corresponding 1/2. Red's not working all that great today. Out front to balance the fact, so now we've multiplied by 1. So that's the multiplicative identity. And then we would go on our merry way doing u substitution, and we'd end up with the natural log of the absolute value of x squared plus 3 plus c. And that would be our answer for this. And you can do that type of problem already. What I would like to talk with you about is, what if the situation was slightly different? Instead of us having x over x squared plus 3, what if we had a situation like this? We're going to cross that one out. What if we had 1 over, let's just say, x squared, I'm going to change this slightly, x squared minus 4 dx. Okay, 1 over x squared minus 4 dx. And we were going to try and do the u substitution here. Okay, well, we would look to see if u could be equal to x squared minus 4, and that would make du equal to 2x dx, again, just like before. Okay, but our problem is that we don't have an x up in the numerator that we could just double like we did in this first example. In fact, all we've got up there is a 1. And we're not allowed to put a 2x up here, because that would mean we'd have to put a 2x up there, and that's adding another 0 to our it's just screwing everything up. We're not allowed to put x's outside to balance, to counterbalance. So that's not a possibility, and therefore we've got to come up with another way around this. Okay, and the way that we go around this is through something called partial fractions. All right, now, this is a fancy term, but let's talk about the idea. And in order to do that, I'm going to just switch over for a second. If I asked you to add 1/3 and 1/2, okay, we're going very basic here. If I asked you to add 1/3 and 1/2, you're adding fractions, and you know that what do you need when you're adding or subtracting fractions? Exactly, you need a common denominator. We don't have a common denominator, so the first thing that you would have done would be to get the common denominator. Obviously, that's 6. So you would change the denominators to 6. Yes, I'm imagining you would do that. And you wouldn't leave the numerators as 1. You would actually have to multiply the numerators by the same term that you multiply the denominators. So obviously 1/3 is the same as 2/6, and 1/2 is the same as 3/6, and we would get our answer of 5/6. Okay, so in order to add fractions, we need a common denominator. Okay, and we're going to kind of build off of that idea of this whole common denominator thing. Instead of having 1/3 and 1/2, what if we had 1 over x minus 2 and 1 over x plus 2, and I asked you to add those two terms together? Once again, you would need a common denominator, and the quickest way to get the common denominator would be the exact same manner in which you got this common denominator. I'm guessing you said, oh, well, 3 times 2 is 6. There's a common denominator. It may not be the lowest common denominator. In fact, it was for this problem, but it's a quick way to get a common denominator. All right, so if we want to do the same thing right here, our common denominator would just be the product of these two. So we would be looking to have x minus 2 times x plus 2. That would be our common denominator. So we have to change the first fraction, and we'd have to change the second fraction. All right, and once we did so, all right, then we could actually add these two fractions because they have the same denominator. Okay, now when we change the first fraction, well, the first fraction, the denominator initially was x minus 2. Now it's x minus 2 times x plus 2. So we have a 1 up there, which doesn't really matter anymore, but let's just stick it in there for now. And then we would have to multiply the numerator by x plus 2. Okay, now this fraction right here is the same as that one. Okay, this is just a simplified version of this one. Okay, and same thing right here. We have 1 over x plus 2. Well, the x plus 2 is down there, but we brought in an x minus 2, so we need to bring an x minus 2 up into the numerator as well. And now, I know it kind of cramped it all up here, but this sum is going to be the same as that sum, except this one we can actually do because we have the common denominator. And if we were to do the common denominator, we would have x plus 2 plus x minus 2 up in the numerator, and then down in the denominator, x minus 2 times x plus 2. Okay, so hopefully that's a quick little algebra review that makes sense to you. If it does, that's good, because in essence, we're going to be doing the opposite of this. We're going to break this down the other way in order to do this partial fraction thing. But that's the general information about it. You'll see the process in the next 2 videos where we do 2 examples. But ultimately, what I want you to see here is what we're getting at with this partial fractions is we're going to turn x squared minus 4 into x plus 2 times x minus 2. Okay, and by doing so, we can then break the fraction apart, and that's going to allow us to do our antiderivatives. So in general, partial fractions is going to allow us to find antiderivatives like this, and we're going to do so by basically simplifying the denominator, all right, x minus 2, x plus 2, and then we're going to break it apart. And you'll see that in action in the next video.